name is Chen Fan, and I'm a second-year PhD student in economics at Bonn Graduate School of Economics in University of Bonn. And this video is a video about the Shiny app I created to facilitate the sensitivity analysis proposed in Rambachan and Roth 2022. And for those who haven't read this paper yet, I highly recommend you to read this paper before using this app, because in the app, you will see many terms which are adopted from the original paper, so you need to know what the terms mean. In this video, I will not go over any theoretical part of that paper, but only cover the functionalities of my Shiny app and how you could use it to do sensitivity analysis. Generally speaking, there are 5 tabs in this Shiny app. The first tab is a homepage tab. On homepage, you will see a brief introduction about this Shiny app and an instruction video on how you could use it. Now you can only see a random video from YouTube, but later on when I finish the recording of this video, then I will replace this old one with the new one that I'm recording now. On the second tab, you can do sensitivity analysis for a selected paper which has already been discussed in Rambachan and Roth 2022. And you need to complete several steps before getting the result of sensitivity analysis. Step 1, you need to select a paper to analyze. So here I selected the paper called Rambachan and Roth 2019. I selected because this is a paper that has been specifically discussed in the original paper, like at section 6. They have already done the sensitivity analysis for this paper. So I want to use my Shiny app to do sensitivity analysis for that paper too, and compare compare the results from my app with the results on the paper, and they are assumed to be the same. At step 2, you need to select a method to construct a confidence interval. I assume that all of you have already read this paper, so you know what these 4 terms mean. And at step 2, I used the conditional least favorable hybrid method to construct the confidence interval. And then we move on to step 3. At step 3, you need to define the restrictions on parallel trends. So you need to first define the base choice of delta or restrictions. There are 2 choices on the base delta: smoothness restriction and bounding relative magnitudes. Here I choose bounding relative magnitudes. And sign restriction as well as monotonicity restriction are optional. Please be reminded that you need to choose at least one base choice of delta, but of course you could also choose both of them. And then we move on to step 4. At step 4, you need to enter a vector of m bar or m to define the base delta that you select. So for example, if you only select the smoothness restriction at step 3, then the vector you enter at step 4 is a vector of m. And if you included the bounding relative magnitudes into your base choice of delta, then the vector you entered at step 4 is a vector of m bar. For the detailed definition of m and m bar, please read the original paper. Okay, so here we need to define a vector of m bar. So there are 2 ways for you to define it. The first way is that you could enter an arbitrary vector, and the second way is that you could enter a vector by defining a sequence. Here, I will first show you the first way. So for example, if I'm interested in m bar equals to 0, 0.1, 1, and 2, so I just need to enter the values here. Here is a pop-up message saying that I could not define the vector by both ways simultaneously, because see, we have already entered the vector by defining a sequence here, so we could not do re-enter the vector arbitrarily. So we need to delete the value at the sequence, and then we can do it. the first box. So we will enter the vector arbitrarily. So 0, 0.1, 1, 2. You could enter the value that you are interested in, the value of m bar. And the second way is like you could define the vector by a sequence. That means you need to enter the lower, the upper, and the step of the sequence, right? So here we are interested in like the lower bound is 0 and the upper bound is 2 and the step is 0.5. That means the m bar, the values of m bar that we choose is 0, 0.5, 1, 1.5, and 2. We will use the second way to define the vector. And now we move on to step 5. In step 5, we need to enter a vector of indices to indicate the post-treatment periods that you are interested in. So for example, if you are only interested in the first post-treatment period, then just enter 1 here. And if you're interested in the first 2 post-treatment periods, then you need to add 2 here, but separate the 2 numbers by a comma. And if you're interested in the first 3 post-treatment periods, then you add 3 here and put a comma ahead of it. And as a special case, if you are interested in all the post-treatment periods, then just leave it blank. And for those who have already read the paper, we know that we need a weight vector to define the target parameter of interest for our analysis, right? So here, we give, in this app, we give the same weight to all the periods that you enter here to define the weight vector. That means we are interested in the average treatment effect over all the periods that you enter here. And for those who want to give different weight to the periods, you need to revise the R code which is produced here when the analysis is finished. And then you could revise the L vector here manually and run it on your own R console. Okay, and then we move on to step 6. At step 6, you just need to select an alpha. That means the level of significance. And then at step 7, you need to indicate whether to construct a robust confidence interval in parallel. You may be confused about the definition of what is parallel mean, but you don't need to care about it. So you just need to select no as suggested in order to increase the computational efficiency. And one thing I want to mention for step 8 is that step 8 only appears when you include bounding relative magnitudes in your base choice of delta. If you only select a smoothness restriction in your base choice of delta, then step 8 disappears. You don't need to care about it anymore. So here, because we choose bounding relative magnitudes as one of the base delta, then we need to care about step 8. At step 8, we need to enter the lower and upper bounds of grade, as well as the number of grade points which will be used for underlying test inversion. So you may have no idea what the test inversion means, but all you need to keep in mind is that the first time you run your model, you don't need to change anything to step 8. Just leave the values as what it is. And then you need to click start. And because it may take more than 2 minutes to run an analysis, so to save your time, I will not write here now. Here, I already clicked the started button before I started recording this video. So here, I already got the sensitivity analysis result. One thing we find out about the plot is that the upper bound of confidence interval at m bar equals to 0.5, 1, 1.5, and 2 are exactly the same. You can also see it from the tables here, right? These 4 values are exactly the same. Why? This is an error from computation, and how to correct it? It is because you can find a hint below the plot. The hint is that why we have this error is due to the fact that the upper bound of the grade used for underlying test inversion is too small. That means the default value of here is too small, so we need to increase it in order to get the correct confidence test. But now you may consider what the default value of the upper bound of the grade here is, and we got a hint that we need to go to more and frequently ask the questions for more details. And then we click more and the FAQ, and we go to here and number 5. Question number 5. So what should I do if the lower or upper bounds of the confidence test turn out to be exactly the same for different m bars? It explains the reason, and it also says how the default value is defined. By default, the upper bound of the grade used for underlying test inversion is equal to 20 times the standard deviation of the estimated target parameter. So we need to know what the standard deviation of the target parameter is, and then times it with 20 to find out the default value of the upper bound of the grade. And so we just need to go back here and we click the data file because we have because this analysis has already completed, so we can download the data file of the original paper by clicking the button here, and we will find out the sigma here, because we need to find out the standard deviation of the target parameter, and our target parameter here, as I define, is the average causal effect over all post-treatment periods, and the post-treatment periods is like this. We can find out from here, pre-treatment and the post-treatment. So the post-treatment periods are 5, 6, 7, and 8, and for sigma 5, 6, 7, and 8, and we need to find out the standard deviation of this one. And so you can see like the values here are very small, and you don't need to calculate the accurate standard deviation of the target parameter here. You just need to approximate it and find a value which is bigger than the approximate estimation of your standard deviation. So obviously, I think 1 is obviously larger than the standard deviation of the target parameter over the 4 periods, right? 1 is obviously large enough to define this. So all we need to do is to define the upper bound of the grade here as 1 and start and run the code again. As it may take more than 1 minute to run the code, so I will now wait here. I will just go over to the next tab, and we'll come back when the code is finished. So one thing I want to say is that you could also download the all the sensitivity results by a simple click of the buttons here, and you could also reset the input by clicking the reset here, and if you want to reload the page, you can just click the button of disconnect the app here. Okay, and then we move on to the third tab. The third tab is sensitivity analysis for your own data. That means you could do sensitivity analysis for your own research. All the steps are exactly the same as the examples tab, except the step 1. So in examples tab, at step 1, you need to select a paper to analyze. But here you need to upload your own data to analyze, and your own data should include the estimated event study coefficients and the variance and covariance matrix. I can see that it has already finished, so we can see like the upper bound of the confidence interval now is not the same, so it means it's correct, and we can compare the result to the paper. And on the paper, we can find out that here in figure 5, the right panel is exactly what we have done here, right? You can compare it, and you can compare the values to each other. Like the confidence interval crosses the 0 line at m bar equals to 1, and we can see from here it is exactly the same thing. So that means the Shiny app, it performs quite well, and it shows the exactly same result as those in the paper. Okay, I will go back to the third tab. So you need to upload a data file which includes your estimated event static coefficients and the covariance matrix to do the sensitivity analysis for your own data. And you need to download the example file here and see how your to see how your data file can be constructed. And here you need to design your Excel file by 6 sheets, and each sheet means an object that you need to put into the analysis, and you are not supposed to change the titles of the sheets, and please don't change the names of the variables here, like v1, v2, don't change it, and the beta, sigma, tvac, don't change it. Okay, and then you just browse it here and put your data into here, and then do the same setup as I have showed before in the examples tab, and then click start. Then you will get your analysis result. Okay, but the problem is that what if you don't have your estimated event static coefficients or the covariance matrix? That means you need to estimate these two stuff, right? On that occasion, you need to go to the quick help tab for help. So here you can do your estimation quickly by setting up something, and it consists of 2 different types of the DID. One is called non-staggered, and the other is called staggered DID. And for non-staggered DID, we use the 2 effects to estimate your coefficients and the covariance matrix. And here you also need to upload the raw data file that you have at hand, and click here, example file, and to see how your data file could be constructed. It should consist of 4 different variables: an ID, a time, a D, which indicates like at a certain time a certain individual if it is treated or not, and Y is a target variable that you are interested in. Don't change the names of the variables in the file. And as step 2, you need to select an estimation model, and here we provide 3 different estimation models. The first is OLS, and the second one is GIM. And for GIM, you could also select a family for your GIM, like Gaussian, Gamma, or Poisson, and so on. And we also provide the third way for estimation, like maximum likelihood estimation, and you could also select a family for your MLE. And for those who are familiar with these 3 ways, you know that GIM with Gaussian family and MLE with Gaussian family are exactly the same with OLS. And at step 3, you need to enter a value which indicates the reference periods, because here the time setting is non-staggered, so the reference period is just 1 value. Okay, so here, because in our example file, the time variable has from it is from 2008 to 2015, and the treatment and the reference period is 2013, and so we just enter 2013 here. But of course, you could change it to fit your own data set. Okay, and at step 4, you need to select the alpha to do your analysis, and then you click start. I will just do it here, and non-staggered data form, choose. And I will use OLS, and the reference period is of course 2013, and the alpha is 0.05, and I started, and then I got the event study plot very quickly. And we also have the R code, which you can copy and paste to your own R console to get the exactly same result as we have got here in the app. and you could also download the result by simple click. And the data file that you downloaded from here can be used as input file in Analyze Your Own Data tab. Okay, and also we have a HonestDiD. So in HonestDiD panel, we use the group time average effect to estimate the staggered treatment effect. And still you need to check the example file and how your file need to be constructed. We have an ID variable, a time variable, Y variable, and G. G indicates like when the individual was first treated. So for example, for individual 2, he or she is first treated at in 2016, and for individual 4, he or she was first treated in 2014. Okay, and then at step 2, you need to define if you allow your panel to be balanced or unbalanced, and the suggested one is unbalanced is not allowed to increase the computational efficiency. And at step 3, you need to choose how your control group is defined. The suggested one is not yet treated. For the definition of these two options, you could just hover your cursor here to see the definition. And for the other steps, if you have any questions about the definitions, you can also hover your cursor here to see the hints. Okay. And at step 4, you need to choose the method to compute the group time ATT. And at step 5, you need to enter the smallest and the largest event time you want to observe. And at step 6, you need to select an alpha for your analysis. And here I will also run it. Browse and HonestDiD data form. I will leave all the steps as the default values and click start. We also have an R code, the R code here, and you could use the R code like if you want to fine-tune your R code and run it on your own R console. You could just copy and paste and revise it accordingly, right? So that means if you have more specifications like control variables, nonlinear constraints, and instrumental variables that you want to add into your estimation models, then you need to revise the R code accordingly and run it on your own console. And then you could download the staggered ATT here, which you could use directly in the panel of Analyze Your Own Data. Okay, and in more tab, you can find all the resources that are used to create this Shiny app. And if you have any further questions about the Shiny app, you may find the answers here. And if you have more questions which you cannot find here, you can contact me from the homepage. Like here is my email address, which you can contact which you can use to contact me. Okay, you can also report an issue here to my GitHub page, because I have already uploaded the source code of this Shiny app to my GitHub. Okay, and thank you so much for watching this video. I greatly appreciate it, and thanks so much.